So the first thing we'll start with today is elasticity. Okay. And plasticity, and the relation between stress and strain beyond the elastic limit. So for any type of elasticity, whether it is tensile or longitudinal, or it is shearing, or it is volumetric stress and strain, for any material, if we do what is called stress testing, experimental analysis or data analysis from experimental data of stress versus strain, then typically we will get a relationship between stress and strain, which will be something like this. It will be linear up to a certain portion, and then beyond a certain value of stress, it starts deviating from the linear behavior, and it starts straining with a larger amount of strain as compared to the expected linear behavior. So the expected linear behavior is along this line. You can see the strain starts to deviate in such a way that there is excessive strain for a certain amount of stress. Okay. And then there is also a situation where this is a two-way line. So that means that if we bring the material up to a certain amount of deformity and then relieve the stress, it tends to come back to natural shape. But beyond a certain point, that does not happen. So let's say that point is over here. So beyond this point, the graph is like it goes in such a way that if you bring the stress down, it shows a permanent deformity. So the reverse side graph is like this. And then eventually there reaches another point where there is something called a yield point, where even a minimal amount of stress causes a sort of horizontal kind of, so the material basically just behaves completely like a fluid and strains indefinitely before there is a breakage created. Okay, so these are the various important points on the graph. Okay. So make the graph first and we'll discuss more about that. So this could be longitudinal stress and strain, this could be shearing, this could be volumetric, whichever be the case. But typically any stress analysis or any experimental data based on stress analysis will give this kind of a graphical analysis. Okay, so I'll just explain the various points on the graph. Okay. Just make a note of the graph first. Okay, so let's understand the various different points in the graph. So the point P is called the proportionality limit of stress. That means the value of stress at the point P, that is the proportionality limit. So it is for stress less than equal to the proportionality limit. Two important things happen. One is that stress and strain are proportionate. So the material behaves according to Hooke's law. And secondly, the material is elastic in nature. So it shows the elastic property. That is, if stress is zero, is back to zero, then strain will also be zero. So the material has a tendency to retain its original shape if we release the stress. So up to the proportionality limit, both these things are happening. Okay. Stress and strain will be proportionate to each other. There will be a linear relationship between them, or proportionality limit. So Hooke's law is obeyed, and the material is displaying the elastic property. Okay. So make a note of this, then we'll discuss further. Okay, now the next aspect, or the next aspect of the stress and strain graph, that is the elastic limit. Stress. Okay. So what happens is, it is the value of stress at the point E on the graph. Okay. Now this is the maximum limit of stress for which the material retains its elasticity. So basically what this means is that for stress less than equal to elastic limit, okay, the material is not permanently deformed. Okay. But at the same time, you have to understand one more thing, that for stress greater than the proportionality limit, Hooke's law is not okay. That means the strain becomes disproportionate, or you can say non-linear with respect to stress. So that is the significance of this other point, which is the elastic limit. So all our numerical analysis that we do in this chapter is always assuming that the stress is within the proportionality limit. So not only is the material retaining its shape and its elasticity, but it is also obeying Hooke's law, that is stress and strain are proportional. Okay, so now let's understand what happens when the level of stress goes beyond the proportionality limit. Sorry, beyond the elastic limit. The material loses its elasticity and it displays plasticity, that is the tendency to be permanently deformed. And also on the graph, that yield point, so just a minute, I'll reshare the graph. Yeah, so, and y is called the yield point. It is the value of stress at which the material starts to get severely strained prior to fracture or breakage. At the weakest point. So basically, the moment your stress has become greater than equal to the yield point stress, the material will fracture. And B is the breaking point. So all this comes from experimental analysis. Okay, so all these values, the graph, okay, then the values of proportionality limit, elastic limit, yield point, and breaking stress. These all come from statistical analysis of stress testing experiments. Okay, so this is just factual things you relax. Okay, so this you should have an idea of the definition of each of these terms. There won't be any numerical analysis and things based on this. All the numerical analysis is within the part of the graph which is linear, that is from O to P. And then one final thing that you need to understand about the graph of stress versus strain is that, so let's just pick up that graph. For the region of the graph, which is only from up to the elastic limit. If we are looking at the stress only up to the elastic limit, then at any point, if this is even beyond elastic limit, if this is the level of stress, so this is the strain. Now this area under the stress versus strain graph, it represents energy density. So you can already see that for stress less than the proportionality limit, half into stress into strain was equal to the energy density. So this is anyway the area. Okay. But also for stress greater than the proportionality limit but less than equal to elastic limit, the area still represents the energy density. And the moment our stress becomes greater than proportionality limit, greater than elastic limit, there are non-conservative dissipative forces associated with plasticity come into action, dissipating mechanical energy. Okay, so this is another important aspect to understand related to the stress and strain graph. Yeah, Vinith, I will scroll up. This is the part you wanted to.
Done, sir.
Yeah, Vinith, you finished?
Yes, sir.
Oh. Now coming back to the relationship between stress and strain and the area under the graph. So you can see that up to the proportionality limit, the area is going to be a triangle's area, which is half base into height, which is going to give you the formula that we had developed earlier, that half into stress into strain is energy density. But even beyond the proportionality limit, as long as our uh, stress is within the elastic limit, okay, we're still going to have that same relationship that the area under the graph, it will not any longer be given by the formula half stress into strain, because you're going into the curved region of the graph. And you can see from P to E, the shape is non-linear, but still the area under the graph is a measure of the energy density. Whereas the moment the level of stress crosses the elastic limit, then we don't talk about elastic potential energy or energy density anymore, because the material crosses its behavior from elasticity. It crosses over from an elastic behavior to a plastic kind of behavior, and there is permanent deformity caused by non-conservative forces. Okay, so that is about the elasticity beyond proportionality limit and beyond elastic limit, etc. Now coming back to longitudinal stress and strain that we were discussing last time. So we will see that there's another type of analysis that we can do. We can do a comparison of a longitudinal elastic material, okay, like a metallic wire or even a rubber rod kind of thing, and an ideal spring. And we can see that we can do a direct comparison between the properties of these two kind of things. Okay. So, for example, if we have a material of natural length L, area of cross section A, and Young's modulus Y, and we are comparing that with a spring, an ideal spring or spring constant K, and natural length L. Now we know that in order to either extend this or compress this, okay, we need to apply external force, which will balance the internal tension. In this case of elongation, or in this case of compression. We need to apply a compressive external force like this. So this is that kind of situation. It is an isotropic linear kind of material under uniform stress. So in that case, we have the relationship that stress upon strain is equal to Young's modulus. Okay, so from this we have the amount of external force is balancing the internal restorative force, which comes out to be AY by L into delta L. So this is the relationship between force and the amount of deformity. And we also saw that the elastic potential energy was which is why from this we saw that the energy density was so anyway, now if we compare that to the situation of an ideal spring, so in the case where we are elongating the spring, you can see that the external force has to balance the internal conservative restorative tension, or in the case where the spring is compressed, again the external force has to be compressive in nature and exactly balancing the internal restorative force. So here again the formula is that the external force, which is equal to the internal conservative restorative force, is equal to Kx. Okay. And the spring's potential energy is equal to half Kx squared. So you can see that there is a direct correlation between these two terms. Okay. So you can see that this behaves like this. It is an equivalent spring. It behaves like an equivalent spring of equivalent spring constant Ay by L. Okay. And the deformity is basically the delta. So when we are solving questions related to longitudinal elasticity of materials like this, we can actually visualize, or we can do the numerical analysis by replacing the longitudinal material under this kind of uniform stress and strain with an equivalent spring, an equivalent ideal spring. And the equivalent spring constant would be given by this formula, Ay by L. So this becomes very useful then. Okay, so then not only is it used, it's easy to remember these formula by relating it with an equivalent spring constant, but it's also easy to apply the concepts when there is combination of materials. Okay. So we'll discuss about that next. Yeah, Kevin and Amog, I'll scroll up. Just give me a moment. This part you people wanted to. Okay, okay. Just let me know when you're done. Then we'll come back to equivalent spring constant concept. Okay, okay, right. Okay, so what this does now, people, is that it makes analysis of questions where there's a combination of materials very easy. So, for example, suppose we have something like this. So this is, let's say, what we call a coaxial cylinder kind of thing. Coaxial cylindrical material. And then that is also against another material like this. So this combination is on the floor. Against a rigid wall like this. So this thing is actually a coaxial cylinder, metallic. So its cross section actually looks like this. This is the cross section. And this is solid metallic cylinder. Now this one, this inner core is made of material of Young's modulus. This much. Outer layer is made of Young's modulus. This much. Okay. The inner core has inner radius and outer radius 5 centimeters. This one is made of Young's modulus. This much and radius 5 centimeters. Okay. And this has a natural length L prime and this has natural length L. This has, so these are the natural lengths. Now what we are going to do is we are going to push this with some external force such that the point of application of the force has to have certain displacement. So F external is applied as shown above, so that the surface at which this is applied displaces by S equal to, let's say, 1.8 centimeters to the left. So we want to find out how much external force is there. Okay. Then stress in each of the materials. And we also want to find out the displacement of the junction. So just try this question out, and now you'll see that you can actually convert this question into an equivalent combination of springs and make it very easy to solve according to that. So you can use that method of converting into equivalent string. Okay, Ansha, I will scroll back up. Just let people take down the data of this question. Then we'll go back to the previous section. Okay, so I'm going back to the previous section. Comparison of spring.
1 minute, sir. Can you just show the question?
Okay, finish with this first.
Yes, sir. Done.
Okay. Okay, I have resumed the recording, and this part I think you must have finished with. Okay, so let's come back to that problem. So how we'll solve this problem is, as I was saying, we will convert this into a equivalent system of springs, okay, using that formula that equivalent spring constant is Ky by L. Just try this out by that method, we will discuss. Okay, so let's understand what we'll do here. So the coaxial one, the coaxial cylinder, okay, let's say the core part is having spring constant K1. So that is going to be and the outer layer will have spring constant using this, and for the coaxial cylinder, the K will become the parallel combination of K1 and K2. Because what is happening is that the net tension is equal to the tension in the first one plus the tension in the second one. And So we will take the coaxial cylinder and replace it with a combination of two strings first. So we will first convert this into this kind of a combination. And then like this. Let's pick up the values. So inner and outer radius were 2 and 5 centimeters. Young's modulus was 3 and 6. And natural length was 5 meters. Right? Yeah. अच्छा हाँ हाँ आज नहीं होगा बाहर कौन सा अच्छा यहाँ क्या स्टेशनरी शॉप में था आपको लिए नहीं है आसपास नहीं है कुछ Okay, so our equivalent spring constant. So first, let's work out K. So now our K equivalent be such that 1 upon K equivalent is 1 by K plus 1 by K3. Let's limit this one. Okay, so this will be the equivalent spring constant. So now the external force we need to apply will have to be the equivalent spring constant multiplied by the displacement, where x will be the displacement of the point of application of the external force. So from that we can see that the amount of external force we need to apply will be this value. Wanted a displacement of 1.8 centimeters. This is the amount of external force. Okay. Now, once we get this external force, we can also see that this external force will be equal to the tension in this spring, equal to the tension in this combination. So this external force is equal to T3, which is equal to T1 plus T2. Where X is the common displacement of 1 and 2. So T1 is to T2 will be equal to K1 is to K2, which you can see will be what is the ratio of K1 and K2? It is 1/21. Therefore, T1 will be this much, T2 will be this much. Okay. And from that, we can find the stress in each one. Okay, I made some mistake in the value of K1, is it? Let me check. Oh, yes, it should be 12 pi. Yes. The ratio is actually 2:21. So this will change. This will also change. So this value you just change it to 4.604. Should be getting something like this. Okay, and then this ratio will become 2:21. So this will become like this. Okay. And then also from this equation, we'll find the value of x. Okay. And that x, which is x1 equal to x2, that will be the displacement of the junction. Because actually that x plus x3 is the total displacement, which is 1.8 centimeters. Yes, there was an interruption again. Anyway, so hope you understood the application of this question. So basically, once you got K1, K2, and K3, you can see that you got the equivalent spring constant, and then basically x plus x3 would have been your net displacement, which is 1.8 centimeters. This x is the common displacement of these two springs. Okay. So now you can see that that kx will be equal to k3 x3 because this common tension, I mean this net tension in that parallel combination is equal to T3, which is equal to external force. Okay. So x is to x3 is k3 is to k. So from that you can see that x will come out to be times this. Okay. So from this ratio, we'll be able to work out the last part, which is the basically the displacement of the junction. Okay, so this is the way to deal with this type of question. Now, another concept question where the displacement of the junction concept becomes important. Remember last time we were discussing about thermal stress. So next we will see a question based on combination of materials under thermal stress. Okay. So let's say we have two metallic rods which are made of different materials having different natural lengths, okay, but identical cross sectional area. They are just placed against each other like this. Supported by a horizontal surface. And between two vertical walls. So this combination is under zero stress at room temperature. So there's a wall here, there's a wall here. Now this length is 5 meters. This length is, say, 3 meters. This is rod A and this is rod B. So rod A, it has a natural length of 5 meters. At room temperature. And the rod is made of material which has Young's modulus. Okay. Coefficient of linear expansion. Okay. And cross-sectional area. They both have a common cross-section. Now rod B has natural length 3 meters at 27 degrees C. Okay. But also has Young's modulus of elasticity. And coefficient of thermal expansion. Okay. So if both rods are under zero stress at 27 degrees C, find the displacement of the junction and tension in each rod at a temperature of 87 degrees. That is 50 degrees higher than this. Both these things we have to calculate at this. So realize that the tendency for the first rod to expand will give it a tendency to push the junction towards the right, and the second rod's expansion will give it a tendency to push it towards the left. But one of them will be dominating over the other because of its material and thermal properties, both elastic and thermal properties, and therefore the junction will end up moving either towards the right or towards the left at a new equilibrium position, which will be established at 87 degrees C. So accordingly, we have to calculate the displacement of the junction and the tension in the rods. Just try out this question, people will discuss. Okay, so now let's say that suppose we assume that the junction displaces by a certain amount s in this direction. So we don't know whether this is the correct result or it should be in the opposite direction. But if we get s with a negative sign in our answer, it will mean that the direction should become opposite. If s comes out to be positive, then our answer is correct. Okay. So what will happen is that at the new temperature, so this is at theta naught, but at this new temperature, theta naught plus delta theta. Okay, the length of this rod, let's say L1 prime, that is becoming 5 plus s. And the length of this rod is becoming 3 minus s. But both of them will be in a compressed state. And the junction has to be in equilibrium. So what is happening is that at theta equal to 27 degrees C, the rod A has a natural length of 5 meters. At theta equal to 87 degrees C, the rod A has a natural length of this much. Okay. Whereas at this temperature, rod B has a natural length of 3 meters. At this temperature, rod B has a natural length of this much. Okay. So these are the natural lengths. But they also have, at this temperature only, the compressed length L1 prime of 5 plus s. And this one has, at this temperature only, a compressed length of this much. So you can see that at this temperature, the strain that rod A is under is equal to its natural length minus its compressed length divided by its natural length. So that is this value. This is the longitudinal strain in the rod A. And similarly, the strain in the rod B is equal to its natural length at this temperature minus its compressed length. That is the change in length divided by the natural length. So this is the strain that rod B is under. Okay. Now we'll do a bit of approximation here. In the denominator, what we will do is in this 50 alpha is very small compared to 1. So therefore 1 plus 50 alpha A will approximate as 1. Similarly here 1 plus 50 alpha B will approximate that as 1. Okay. So further solving this, the longitudinal strain in A will become 5 into 50 alpha A minus S upon 5. Whereas the strain in B will become 3 into 50 alpha B plus S upon 3. I mean, these will actually be like this. There will be the original natural length into alpha A delta theta minus SA S upon natural length. And this will basically be the original natural length into alpha B into delta theta plus S upon the original natural length. This kind of expression. Okay. Now we will relate the strain with stress and stress with tension, and we'll understand that in equilibrium position, the junction should have equal tension acting from both the sides. So the tension in rod A should be equal to the tension in rod B, and equating that will give us the value of S. And finally, if S comes out with a positive sign, that means our assumption is correct about the direction of the junction's displacement. If it comes out with a negative sign, then we'll have to assume that our direction of displacement has to be reversed. Okay, so now we can understand that stress is going to be strain upon Young's modulus. Okay. And similarly, the stress is upon Young's modulus. So same area of cross section, but same amount of tension. So now comparing these two equations, you can see that you can also separate it like this, that Oh, sorry, my mistake. It's into Young's modulus, not divided by Young's modulus. Strain is stress upon Young's modulus. Stress is strain into Young's modulus. So area also cancels out and we get this relation that so this factor determines which direction the displacement occurs in. The product of alpha into Young's modulus, whichever one has a larger product of these two will have the dominating factor. So the displacement will be given by this. So I have worked out the question parametrically. You can substitute the values in there, or you could have also done the question with the substituted numerical values from the beginning and come up with a numerical answer. So according to whichever one has the larger product of Young's modulus into alpha, it will have a tendency of creating a larger pushing force and accordingly it will dominate. So the displacement of the junction will happen accordingly towards the right or towards the left. Okay, so you can check this out. So with that, people will conclude today's session. Next time, we'll pick up some more questions related to elasticity, especially modulus of rigidity and this thing, and bulk's modulus of elasticity, volumetric stress and strain, etc. However, we will also be able to start surface tension in the next lecture. So along with questions of elasticity, we will also discuss about surface tension, possibly about viscosity also. Right. With that, we bring an end to today's discussion. Wish you all the best and thanks for attending, people.